Okay, so here we have a problem that's kind of calculation heavy, but it does a good job of illustrating the relationship between a magnetic field and the current induced as the magnetic field changes, which is why I selected it. So the first parts are just some straightforward calculations to make sure you kind of understand the key terminology and can read the graph. So first, we have our graph here. Magnetic field, time, and it looks something like that, right, where each tick mark will be a second. Right? And we have values here as well, but I'm not going to write them in. It's just going to get messy. So that's our magnetic field, and so we want the value of the flux through the loop at time t equals 3 seconds, which is right there. So we have to look up the definition of magnetic flux on the equation sheet. The flux equals B times A. Now, specifically, right, actually I should be clear, BA cosine theta. But we're told that the field points straight up, so the area and the field are parallel. So this is just BA. So at 3 seconds, we can read the magnetic field value off the graph. It's 0.2 Tesla. And in the problem statement, we're told that the loop has an area of 0.3 square meters. And so we just multiply those two numbers, and we get 0.06 Webers. Again, if you don't remember that unit, you could write this as Tesla dot meter squared. That would be totally fine. So that's the flux. Next, we have to calculate the magnitude of the EMF induced in the loop from 0 to 2 seconds. So that is this time range. So we have to remember what equation relates EMF and changing magnetic field and all that. And it's not specifically just the changing magnetic field, it's the changing magnetic flux. That's Faraday's law. Epsilon equals delta phi over delta t. So the change in flux divided by the change in time. So we just calculated what flux conceptually is. And we know the angle is not changed, so I'm just going to do delta BA, delta t. But the area of the loop is also constant, so the A can come out of that differential. And so then we're left here with something that should be obvious on what it is on the graph. And what that is the slope. So I need the slope of that graph. And I actually, it's probably easier just to read data points off, but it's the slope, conceptually. So the change in the magnetic field is 0.2 minus a negative 0.2 Tesla, and the change in time is 2 seconds. Right, that's the slope of my graph, and the area is still 0.3 meters, or meters squared. So we can plug all that in, and you're going to get 0.06 volts. Right? It is important to note, right, I picked t equals 0 and t equals 2 seconds here. I could have calculated the slope by picking the t equals 1 point and the t equals 2 second point, or the t equals 0 and the t equals 1 point. As long as I keep the numerator and the denominator consistent, then it's fine. Okay? So, 0.06 volts. So now we need to kind of put all this in a graph to plot the current as a function of time. And so we've got a kind of a start on it from what we did in part B. So there's clearly three regions in this graph. I'm going to box them all in different colors. there's clearly three regions in the graph because all that really matters is the slope. So we can calculate this induced EMF in those three parts, then we can make our graph, right? There's three calculations we have to do, and we already did it for the yellow box in part B. So in that purple box, I'll use purple for this calculation, the induced EMF, same equation, but the magnetic field does not change, the area does not change, so phi does not change, so it's 0. Right, so I equals 0 in that region, which is from 2 to 4 seconds. And the other one, the pink box, from 4 to 6 seconds, and once again the area is constant, so this is the change in the magnetic field as a function of time. So our final magnetic field is 0, our initial magnetic field is 0.2, our time interval is 2 seconds, and the area is still 0.3 meters squared. And so this induced EMF is going to be negative. Oops, I realized that I've made a sign error. Just a sec. Yeah, so I'll go back and correct this on the other one in a second. So part B is asking for a magnitude, which is why it's a positive value. But remember, Faraday's law really is that there's a negative sign in here. So, right, there's that negative sign on the equation sheet. So we're going to get a negative times a negative. So this is going to be a positive value, specifically 0.03 volts from 4 to 6 seconds. And so if I go back, actually I'll rewrite it here. So in yellow we already calculated that the magnitude of this, which is then a negative 0.06 volts, right? Because now I care about the positive and negative values for the actual graph. So how do we relate these voltages to currents? Well, we need a resistance, which fortunately we have, 0.2 ohms. So I02 for 0 to 2 seconds is epsilon over R, which is negative 0.06 divided by 0.2, which is 0.3 negative. We already calculated the current from 2 to 4, right, because it's just 0. So the current from 4 to 6 is also the same thing. And so now we have our three sort of regions calculated. We can make the graph. So the current and the time, those are 6 seconds that matter. So actually let me make this a little bit more obvious that it's a negative sign, not part of the equality. So right, our first result is that we have a negative current for the first 2 seconds. Then we have 0 current for the next 2 seconds. Then we have a positive current, but a smaller value. Right, so something kind of like that. That's what it should look like. And then you should label everything very clearly. Right, this value is negative 0.3. This positive is 0.15. And you should label the seconds as well, like so. Okay. Although again, they've done a lot of that on the graph for you, so you don't have to worry about units or anything like that. And that's the induction question.